This video is part of a course on food physics, of which this is the theory section. This introductory subsection belongs to the governing equations of single-phase transport, and that is just one of the types of theories that are included in the theory section. This short video does not give any equations or anything. It's simply a context and an overview of the physics. The immediate follow-up video is the derivation of equations for heat transfer. It's nice to see the big picture of all these equations that we are about to develop for single phase transport. Where do they fit in the big picture? To see that, we have this diagram that shows scientific understanding of anything, and certainly food is one of those anything. It sits on a three-legged stool: theory, modeling and simulation, and experimentation. So theory is one of those pillars of science, and it gives us the framework to understand a process or a product as part of a larger, better understood science. Now we could use theory in modeling and experiment and simulation, or we could use theory to understand experimental data. But the theory stands by itself, and the equations that we are trying to derive, they are part of this theory. We would have to make adjustments in those as we use them in modeling and simulation. That's a separate topic, a separate module altogether. But right now we are just talking about the fundamentals. How we use this theory, how we use these equations can be seen in a simple example. So let's take a food process like canning. So inside this, there's going to be these cans, and let's just say it's solid food inside. So what you're seeing in the diagram is a physical process of heating from the sides of a food material. This is physical world. From there we get to its mathematical equivalent. So now we can say, well, it's heating the same way from all sides. So then we can think of it as a symmetric, and so all I need is this quadrant with heating temperatures on the side, and in the quadrant I'm going to use the heat conduction equation in R and Z direction, and it's a transient process. So this is the simplified mathematical equivalent of a physical process, and this is called problem formulation. When we try to formulate the problem, the real world problem, into math, we need the equations. We need to start from the equations. So that's why we are deriving these equations. Now the equation that I just showed you in the previous slide, do you wonder where it came from, or is that part of a set of equations? Are there choices? Do we have choices in choosing that set of equations? So there happens to be a range of equations or ways to describe physics, and that is shown in this diagram, starting from least complex to the most complex. So this is the least complex, and this is the most complex in this continuum of uh, describing physics more and more mechanistically this way, more and more mechanistically. The equation that I showed you and the equation that this chapter is about if sits here. So these are single phase equations that are distributed as opposed to lumped, and they are certainly a whole lot better than the lumped, meaning they can describe more details of the physics, but they're also much less complex than the multi-phase porous media that sits on the other end of the continuum of models. So this chapter is about things at this level, and I would like you to see how that fits in the big picture of modeling approaches. Every one of these approaches is correct to a different level, and then this one certainly has its place. The equations that we will derive are kind of directly applicable to very simple systems like this one. So for example, if you're heating a pure liquid and a thin liquid, or a solid where we do not have to think of different phases of the solid, like solid and liquid or gas. We don't have to get into any of that. Uh, the equations that we will derive really are this. They belong to this simple set. However, it is applicable to a very large group of products. The equations that will derive are the most used equations. And how do they get used to a much larger class of problem is by way of averaging thing, by way of thinking of averages of these single phase equations. Another way that the single phase equations are useful is when we have situations where separate single phase equations can be used simultaneously. So for example, in this peas with water, we could do the solid phase and the liquid phase simultaneously. So that's another way that the equations that we develop, they may look simple, but they can be used in a lot more complex situations. Here's an example of the simple equations that we'll derive can be eventually used for more complex systems. So for example, the equation that we will derive is not, I tell you, it's not valid for a complex system such as bread that has gas and liquid and solid and also pressures develop and so on. However, if we think of, let's say, the heat equation for bread baking, so we cannot use the heat equation directly. So eventually, in different modules, we explain how we can think of the heat equation, the temperature of bread here at one point can be thought of um, combining, averaging a heat equation for solid, heat equation for liquid water, heat equation for water vapor, and heat equation for air. Each one of them are individually chosen from the equations that are derived in this chapter. So the point is, the equations that we derive here, they may not be directly applicable to bread, but they will be ingredients, they will be the building blocks for the more complex equations that we could use to describe a more sophisticated version of the physics of food processes. It is nice to have a preview of the chapter that we are getting into on single phase. When we are done, we will have three equations, and those three equations that we developed are for heat transport, mass transport, and fluid flow. And those equations, as we derive, we will have these different terms that we clearly relate to the physics involved. So we discuss where these terms come from, what is their meaning, when can we ignore it, when do we have to keep it. So this way we relate the physics to the math and be ready when we would have to be applying it to a real process. Although we will derive the heat equation, the mass equation, and even the flow equation, this set of videos or this module is not a replacement of even an undergraduate course on transport processes. And there's going to be a very simple version that you will see here. And if you're looking for more detailed version, when you hit the limitations and you need to see more detailed versions, there are many excellent transport phenomena texts exist. But of those, this is the one that almost every other book kind of started from. This is the most used, most recognized textbook, and this is where you are referred to for more details of the equations. Now, of course, there are other transport phenomena books of different flavor, different emphasis. For example, there's one by the author, and it has more food examples, and it also emphasizes problem solving. But there are many such books. And most importantly, if you are looking for a more detailed and more complete set of equations, details of derivations, and so on, this is where you want to go.